Alright, so let's start the second part. So what did we get in the first part? The equation. We have an equation that we can read from the chart or from the table, and that equation will give us the efficiency as function of T inlet minus T ambient over the incident radiation, right? And so those are the true input to the equation, and then we can calculate the efficiency, multiply the efficiency by the incident radiation times the area, you can get Q dot useful. So this is the collector, The collector will be something like this, and the water would usually be in a closed circuit. So that water, you don't drink that water, you just send this water in and out, because you will get rusted, or maybe actually you would like this liquid to be antifreeze. We'll have antifreeze so that it can survive in the winter. And then in a heat exchanger, you will circulate with your tank, right? And so now in this tank, now you can use that water then for using, for heating or for drinking or for whatever. And most of the time, you will always have a electric auxiliary unit, right? They will have an electric auxiliary unit just in case the sun is not there. Then that mini storage can get some help from electric heating. Right? Questions? So this is the layout. So now let's see what how useful this equation is and what can we do with it. Alright? So again, you will given a data sheet for that heater, and you are after those two numbers, the intercept and the slope. Okay? And so with the intercept and the slope, you tell yourself, I got my equation. I got this and this. Right? Efficiency on one side, and the T input minus T ambient over the incident radiation on the other side. Okay? So typical problems. Typical problem. Calculate the efficiency, and the Q useful. Of course, if you know the efficiency multiplied by the input radiation, you get your Q useful. So he's asking for the same thing. Alright, and he wants you to do it for each hour in what? In this place, Tulsa, I guess, 32? No, we are 36, right? So 32. And beta, that is the tilt angle, 32, and January 21st, so you can get the delta. And he give you T input, 58 degree, and he give you the T ambient. So that is how the temperature will change during the day. Okay. So usually when the calculation is repeated over and over, you are better off using an Excel file, because once you have the equation, you just like copy it. So here is the time during that day from 7 a.m. all the way to 5 p.m. T ambient is changing according to the formula he gave us to us. So actually he said it at 8 a.m. and noon, and so we did what in between? Linear interpolation between 25 degree at 8 a.m. and 45 degree at noon. And so you go from 25 to 45, you just basically split the temperature. And you do the same thing in the evening. Backward. Okay. T input is always fixed at 50 degree, 58 Fahrenheit. And now this the watt per meter square. Or in here it's BTU hour per square foot. So this you will get it from where? From the table of that particular city for that particular tilt. Okay, that's how much incident radiation is falling on your roof. Okay, so now with T ambient and T inlet and I, you got yourself those three guys, T inlet, T ambient, and I. So all you have to do now is calculate the efficiency from the equation, and Q useful would be this efficiency multiplied by that radiation times the area of the collector. Okay, and this is done twice because I was doing it with the two sets of equation. So I was doing it with the second order slope and the linear, and we can see that both calculation end up almost the same. So he wanted the efficiency every hour. We got that. He wanted the Q useful, and we get this by multiplying the efficiency times the incident radiation times the area. But if you calculate all those Q useful, you add them, that will be the total collected during the day. So you get this much BTU in the first hour, this much BTU in the second hour, this much BTU in the third hour. If you add all of them, that will be the total BTU. That's what he said over here. The percentage of incident solar radiation collected. Let's read this. The percentage of the incident solar energy collected. Right? So when you calculate the total, you divide over the incident radiation, you can get how much did I collect at the end of the day. Did I collect 30% or 40%? Okay. Does this make sense? So this is not just what's the efficiency every hour, it's the efficiency during the whole day. If I put this collector for the whole day, how much he will capture from the incident radiation. So you calculate the efficiency every hour, Q useful every hour, you add all the Q useful, and you get yourself, here's what I did at the end of the day, divided by the incident radiation, that's the percentage collected. Okay? Of course, if there was an efficiency for that day, like you would say, what is the average efficiency for that day? That would be nice. You multiply this by the incident radiation of that day, you will get, but because the efficiency change with the incident angle, and because the temperature of the air is changing during the day also, the efficiency is not the same every hour. Right? So using that equation allow you to accommodate for all those variation. Allow you to accommodate for the change in the theta I, allow you to accommodate for the variation in the ambient temperature. Okay? So this is the part where I say I got the temperature by interpolation, because I was only given the morning, the noon, and the evening. And that how much BTU is falling on the roof, you need to find a table like this, where it say, well, at that place, 32 degree north, that's what he said, and when the plate was at 32 tilt, this is how much radiation end up falling. 106, 193, 256, those are the number over here. 106, 193, 256. So you get the radiation falling on that particular roof. Okay? You got that? Right? Okay, and so this is just, he's putting the number for you and he's using the efficiency, right? Efficiency equation, and he got the FR tau alpha, that's the intercept, and he got this guy, that's the slope, and he got those directly from the table of the chart. Okay, and here is efficiency, and key useful is each efficiency multiplied by the incident radiation, right? And key useful is basically this. And when he add all the Q useful, then he will be able to get what is captured. This is the part when I say don't use the aperture area. Wrong. Use the gross area, because that's how the efficiency is defined. Okay. And finally, the percentage of the captured radiation is how much did you collect over how much did fall over you all day long. Alright? So this was one approach. This approach was, let's calculate the efficiency every single hour. Let's find the angle incident radiation every single hour. Fix the efficiency curve. Find the T ambient. You can tell this kind of analysis is really useful for a very detailed analysis. Huh? This is, you have to do this for every single month too, right? So this is one approach. The second approach is called the F-chart method. Okay, and so this F-chart method say, I'm not going to calculate hourly variation and the temperature of the air every single hour. This is just too much. I want an average numbers. Huh? So this method basically calculate what will happen during January, period. Okay, not every hour, not every day, but just in monthly average. Okay, so this chart may look really complicated, but it's a piece of cake. Okay, the point behind this chart is to find using the y-axis, and we'll see how we calculate this, and the x-axis, you need to end up intersecting the x and y. You need to fall on a point, and this point you read what curve are we on. So if I am here, that is f.5. What is f? The f is the monthly load by solar divided by the monthly total load of the building. That f is basically the percentage of the load met by the sun. That's ultimately what you would like to get. Am I gonna be able to meet half the load by the sun, and then the other half we need electric heater for it, or we gonna meet 100% of the load by the sun? Okay, so the method finish by, if you find the x-axis and y-axis, you basically end up here. If you anywhere in this curve, that means that your f is 0.8. That means 80% of the load will come from the sun. Just buy yourself a small electric heater to cover for the 20% that's not made by the sun. So now, how we can get the x value and the y value? You know, how could we tell that x is 9 and y is 1, so that we will end up intersecting here and say, you know what, our f is 0.4. So the definition of x and y, it's Q loss over the monthly total load, and y is the Q absorbed over the monthly total load. So all of them, the y, the denominator is the monthly total load in kilojoule, in kilowatt hour, in BTU, whatever the unit is, that monthly total load of the building, the heating load, the F chart will tell you how much is going to come from the sun. Alright, so now how we calculate the x and the y? There is long formula for them, and the only difficulty in calculating this in the homework or the exams is just knowing the units. Really, it's just knowing the units that you use, and you'll be able to calculate the x and the y, and that's it. Okay, so why this is hard? Let's check what is the values here. So unlike the efficiency equation, which basically account for hourly variation of the T ambient, this one is just the average T ambient during the months. So T average, T ambient average, that is the average in degree C. So over here, he's trying to calculate the Q loss. So what is Q loss? What's the equation from heat transfer? Q is UA delta T. So he's trying to do something similar. You got yourself AU, and here is the delta T, kind of. Okay. So the AC, what's AC? All the collector area. Okay. And so by the collector area, I'm saying here N times A collector. What's this N? Number of collectors. So yeah, if you have a big building, you're not gonna put one heater. You're gonna put a lot of them. You stack them on the roof. You have 20 of them. So then that AC is the total number of collectors, total area of the collector. And so those kind of problems, they usually are written in such a way that they would say, well, how many collectors do I need to meet 50% of my load of that building? Okay, so for that building you want 50%, so that you want to be on that curve. So then you are trying to figure out by trial and error what is the AC, total AC, which is a number collector time one collector area, that will end up making your F equal 0.5, so that you would say I have 50% coming from the sun. Okay, so the number of collector will come in that AC. L is a monthly load, monthly total heating load. Okay, how much heat they want from us. Okay, we said 100, that's fixed, 100 degrees C fixed, and T ambient is the average temperature over there. And FR UL, what is that? That used to be, what's FR UL? Remember? Was it the intercept or the slope? No, it was the slope. The intercept was FR tau alpha. FRUL was the intercept. So it was the slope. FRUL was the slope. But it wasn't FR prime. What's the deal with the FR prime? So they will tell you, well, see, you are not doing it for 1 day or 1 hour, you are doing it for the whole month. So FR prime is 0.97 FR. It's kind of an average for the whole month. So whatever your FR is, your FR prime is 0.97 FR. Okay? Very good. So that's how we calculate the X, basically. Now how we calculate the Y. Okay? So the Y is the Q absorbed. Q absorbed over the monthly total load. Okay? So the FR prime again time tau alpha. Okay, that's the transmissivity times the absorptivity. Alright? And there is a bar on them. You see the tau alpha and the bar on it? The same deal, because it's monthly average. Tau alpha bar is the monthly average of tau alpha, which basically mean just 0.96 tau alpha. So your tau alpha you multiply by 0.96. Your FR you multiply by 0.97. Okay, and that will give you the average monthly. Okay, so now the only thing that's missing, and the only reason why people screw up this problem in the exams, I guess, is this HTN. Okay, so what are we trying to do over here in this Y thing? We are trying to find out what is Q absorbed over the monthly total load. It's a ratio of how much radiation you are absorbed divided by how much you actually need. Okay, same thing over here. This is Q loss over how much you actually need. So to calculate how much you are absorbed, what do you need? You need the number of days, N is the number of days in the months, multiplied by HT, and HT is, and here is the catch, monthly average daily radiation. So people don't get that. What is monthly average daily radiation? Is that the radiation for the months, or the radiation of the day, or what? What does this mean? Monthly average daily radiation. Help. What do you get from this? Monthly average daily radiation. It's the daily radiation. This is the amount of what per meter square or joule per meter square? Daily radiation. What is it? What is the unit of daily radiation? No, joule. What is power? Joule is energy, right? So in order to say every day how much energy did I get, it's joule per days. Huh? So it's monthly average daily radiation. So every day how many joule do I get per day? And it's monthly average, meaning that don't give me the best day of the month, don't give me the worst day of the month, give me the average day of the month. Okay? So this is the radiation of 1 day during the month, monthly average multiplied by the number of days. So those two guys together will end up being how many joule per month divided by how many joule per month do I actually need. Okay? So how do people screw this up? They don't have the right unit. So this will become in joule, this will become in kilowatt hour, or they use watt. They don't know how to get joule over joule, or kilowatt hour over kilowatt hour, or BTU over BTU. Whatever you do, this is just a ratio. So if the load is in megajoule, the top guy also need to be in megajoule. Don't do it in kilowatt hour or any other weird unit. Right? So whatever the unit of the L, HTN should also be the same. Okay? You got it? Very good. And I guess the same thing for the units over here. See, the L is in joule. Okay? Now what is the UL again? Does anyone remember what's the unit of the UL? The overall heat transfer coefficient from the heat transfer course? Watt per meter square Kelvin, right? So this need to be dimensionless. So the watt per meter square Kelvin, the Kelvin get cancelled with the delta T. Good. We are now down to watt per meter square. The meter square will get cancelled with the area, the meter square here. So we are down to what? Downstairs it's joule. That L is in joule. So that UL, which is in watt, need to become joules. So how do I turn it into joules? I need to multiply by time, right? So that's why it has delta T next to it, right? And they will tell you that delta T is the number of hours in the months. Okay, so but the trick here is then, right, so you turn either the U in watt per meter square, sorry, watt, but rather than watt it becomes joule per hour, because usually they will give it you in what? In BTU hour. So then you multiply by the hour. Alright, so I'm not going to teach you unit conversion over here, but what I'm trying to say is whatever the unit of UL delta T, it better be joule, just like the guy downstairs. Or if this guy is in other thing like BTU, then those guys multiplied together need to be in PTU. Thing need to be dimensionless. You do it in UL delta T over L, and you do it over here also for HTN over L. And then you'll be home free. You got your X and Y dimensionless, go to the chart, read the F, and that is the load that you are meeting by the sun. Okay? The chart is hard to read, so they have equation for you to use, and you can see the equation is just y and x. If you know y and x, you can get your f. There are two charts in the book. One if we are heating water in the collector, and the other one if we are heating air in the collector, because sometimes they use this collector for air heating, space heating, right? Air go in, get hot, then send back to the building, right? And so that helped the HVAC system basically, rather than spending a lot of energy heating the building. So here is an example. Calculate the thermal energy you expect to collect from a south facing liquid based, then use the chart for the liquid, don't use the chart for the air. Collector tilted at 45 degree from the horizontal during March. So the south facing and 45, this is to open the chart for Tulsa and look for fixed collector at latitude tilt, so that you will find out the incident radiation, the average radiation, monthly average, daily radiation. Remember, monthly average, daily radiation. So you open during, he said March, so we open the day of the month of March at latitude tilt, and we say how much average kilowatt hour per meter square per day. Okay. The average air temperature 6 degree. What is that? That's the average air temperature over here, 6 degree. The monthly average daily insulation, he already did the job for us. Like, I mean, we could have went to the table and get this number, but he said that is 14.8 mega joule per meter square, not millijoule, right? Mega joule per meter square.
When you say charts, you talk about the charts in the back of the book, right?
When it comes to the F, I'm talking about this. But did I say chart in the context of like table? I was talking about the table for Tulsa where we can get the radiation at different days, or what? What did I say? When did I say chart? The 14.8. So right. So he got it actually from the table for Tulsa. Remember the table that we said here is for every month, here for latitude tilt, here is for latitude minus 15, here is latitude plus 15. Alright. And for that collector, he got FR UL, and then FR prime, you hit this by 0.97. He got FR prime tau alpha, and for that he multiplied by also 0.97. Right? And the collector area is 10. And the monthly heating load is this much. That's the L. That's the one in the denominator. Okay? So all we have to do is calculate the X and the Y, and from that calculate the F. Right? So, and you can follow those numbers at your leisure at home. Right? And you will be able to see how we, again, what is the trick? The units. So look at this, the delta T, the number of hours per month, right? But in order, since he gave me watt per meter square, then my problem now is the UL is joule per second, so I need to multiply by seconds, right? And that is the second in the months. So you can, what is it? 31 times 24 times 60 times 60. 31 day, 24 hour, 60 and 60 minutes, second. Okay? So now this delta T will take care of turning the watt into joule. And downstairs, he give me the load in megajoule. I have joule on the top, I need to have joule at the bottom. So that's why 10 to the power 6. So now joule and joule, my x is dimensionless, and you will guess immediately. I mean, if you use the wrong number, your x will not be in the chart. Your x will be like 3000. Like where is that, right? Will not fit. You will be able to tell. And the same thing for the y. So HT again, what is that? The monthly average daily radiation. So 14.8, 10 to the power 6, and March 31 days. So here's 31. So now this is joule per basically during the months divided by the total load. Okay, so we got x and y. I go to the chart or I use the equation and I get f.84. What does this mean? 0.84 of that daily, 0.84 of that monthly load is coming from the sun. Make sense? So now I could have said this problem, how many collectors do I need to meet the load exactly by the sun? So you would basically have said, well, let me try not one collector, let me try two collectors. And so you put 2 over here and you calculate the F. And when the F hit 1 or higher, you think, we done. We now meet all the load by. In the homework, there's 2 problems. One of them say, calculate the number of collectors to meet 10% of the load every single month. So that basically means you probably need to go for the weakest link, the months with the largest load but the smallest incident radiation, and you need to make sure that this guy is 10%. So basically what I'm saying is that you go and make sure that no month has F less than 0.1. Okay? And in the other part he said, how many collectors we need to meet 100% of the load by the sun throughout the year. Like all year long, we want always to be F1 or higher. So same trick, you just keep playing with the A until you hit 1 for every single month. Okay? Very good. So here, this is a typical homework problem. He said use that collector. So what do we need from the collector? Slope and intercept, right? So that we can get our FR prime tau alpha and we get our FR prime UL. And he gave us the monthly load for every month, January, February, right? And you can see the load is really high in January and December because that's where they need most heating. And so you can tell now if we really make the system meet every single month by solar radiation, probably will be way over designed in the summer. Because the summer we don't have that much load and we have so much sun. So I mean if you design the system so that's why maybe it's not smart to meet all the winter load by solar radiation. Because you just like have so many of them. But maybe you should say, well, I want year long to meet the solar like 20% of the load by the sun or 25%. This way you will meet all the summer. You are not going to run any electric heater in the summer because the sun is strong enough, and you will cover a bunch of the winter, like a percentage of the winter. And overall you basically reduce your electric bill by 25% because the heating comes from the sun 25% of the time, year long. So that's a better scenario, right? So how many solar collectors are needed to meet the load? What is the load? You want year solar heating radiation or fraction to be 60% year long. Okay? And he's saying if the natural gas is $10 per million BTU, how much you would have saved by basically installing that system. So he's trying to convert the joules into dollars. So once you calculate how much is Q useful, that's your conversion. how many BTU, and every million BTU is $10. Then you would say, well, that system every year give me that many dollar that I would have burned if I, or have used if I just used natural gas to heat the house. And then that would be the value of that system to you. If you give me this many, then I'm not gonna pay more than this. Right? If that system saved me $200 per year, then I'm not gonna pay more than $200 per year. So depending on how many years he will live on the roof, 10 years, and if you give me 200 every year, then I'm not gonna pay more than $2,000. 200 times 10 years, 2,000. That's the value of the. And then we break even. I'm not even making money. We just paid exactly what he gave me. Of course, if it's cheaper, that will be even better. Right? So in order to do this, to get 60% of the year by solar radiation, what does he do? So he's using the F chart method, right? So he need the days every month and the load every month, right? The ambient every month, and he's trying to calculate his X and Y. Okay, the X and the Y, same formula, right? And you can see how he went to the table of that heater and he figured out what is the FR tau alpha and what's the FRUL. Okay, and the area of the collector, because he doesn't know how many, he's trying to find out how many. He said the area is one collector times the number of collectors, A times N. Alright? And so once he got the X and Y, he calculated the F. And he had this in an Excel file, or in his case he had it in Mascat, and he basically keep changing the number and he keep looking for the F. Right? And that F is done for every month, but then he can collect. So here is the X and here is the Y, and here is the F for every month. And when you get F more than 1, that basically means F should be 1, because that extra heat, you are not going to use it. I mean, in the summer, if they need 20 megajoule and you generate 25, we are not going to use it, right? It's wasted. Right? So he set them to 1. Okay? And so now those are the correct number. F every single month multiply by the load every single month, you'll be able to calculate Q useful every single month. See, that's what happened. So here is solar radiation and here is the load, and so he calculate the percentage and he keep repeating until he get exactly 60% or higher. Does this make sense? So you cannot do this by hand. You have to do it in an Excel, because you cannot just keep solving over and over. Right? And once you figure out what is the total you collect, which is like basically all the Q useful that you added to each other, you turn them in BTU, and that then you can turn them into dollars, and that would be the value that you're calculating. Question about the F chart? So again, the only mistake that could happen is in calculating the X and the Y, specifically in the units part. But collecting the solar radiation and collecting the temperature is not that hard. Questions?
Is that